Okay. In the last class, we have discussed yes, in the last class, we have discussed about electromagnetic induction, and after that, we will discuss. All right. Let me check first. Correct. Yes, electromagnetic induction. Hello. Last day, we have discussed about Faraday's law of electromagnetic induction, and this situation was discussed that you see here when a conductor is placed in a region of uniform magnetic field, then the free electron available in the bulk of conductor experience no magnetic force because conductor is at rest in the uniform magnetic field. So force equal to F equal to Q into V cross B. As V is 0, therefore force is 0. But as soon as this conductor starts moving in the direction perpendicular to the magnetic field, then the free electron in the bulk of conductor experience a force in this direction. You see here. So electron in this conductor will shift towards this end, making this end negative, and consequently this end will be positive. Therefore, a potential difference get developed across the end of this conductor as long as it keeps moving in the region of magnetic field. And this potential difference is nothing but what? Induced EMF. So, conclusion is that whenever there is a relative motion of a wire with respect to magnetic field, then potential difference will get induced across the terminal of the conductors due to its motion. So in order to moving the conductor in the region of magnetic field, one has to do work, and that much work done is converted into electrical energy in the form of induced EMF. So we have learned that current get induced only when one has to do work in moving the conductor. As long as conductor is at rest in this region, no EMF will get induced in the conductor because no force will be experienced by the free electrons, and hence electron will remain situated at its own place. It will not displace to the end of the conductor. So as soon as conductor keeps on moving in the direction perpendicular to the magnetic field, then along with the conductor, the free electron in the bulk of conductor also starts moving relative to magnetic field. That's why these free electrons experience a magnetic force whose magnitude is expressed as product of charge and velocity of movement and magnetic field. So you see here, V is the velocity of movement of the conductor and B is the magnetic field. The angle between velocity vector and magnetic field is theta. So force will be F equal to Q into V cross B or Q into VB sine theta. As theta is 0, so force is 0. As theta is 90 degrees, so force will be maximum. So when this conductor moves in the direction from north to south pole, no force is experienced by the free electrons in the bulk of conductor. So electron will remain confined to its own place and hence no EMF would be induced in the conductor. But as soon as the conductor moves in the direction perpendicular to the magnetic field, then electron experience a force along the length of the conductors and hence electron shifted to this end. If you apply Fleming's left hand rule, keeping forefinger in the direction blue arrow and middle finger in the direction this one red arrow, then you will see that electron would experience a magnetic force in the direction along the thumb. So actually electron will move in this direction. Electron will get shift to this end. If you apply Fleming's left hand rule, then this terminal will be positive and this terminal will be negative. Actual movement of electron will be opposite of it. This is the conventional direction of conventional current. This is the conventional movement of positive charge, this arrow. But electron itself is negative, so electron will shift to this end and this end will be positive and this end will be negative. So now try to understand. So relative motion of the wire with respect to the magnetic field. Now try to understand with in terms of the activities. The change could be produced by either moving the coil or moving the magnet or both. So moving the coil into or out of the magnetic field, you see here, this is the solenoid and inside this hollow cylinder, there is electromagnetic if current is passing through this coil, but there is no battery connected with the terminal of this, so no current will be there. So as long as this bar magnet is placed kept at rest, no deflection will be in this galvanometer. But as soon as you move this into or out of the cylinder, you will see that pointer of the galvanometer would deflect. So let us check out these activities. Yes. Next one is, you see here, this is the magnet. This is also magnet. North pole this side and south pole this side. And in between this region, there is a coil. Only single isolated coil that we have to sew it up. And this coil is connected with the commutating ring. You see here, two rings are there. Therefore, this will be generator, AC generator. So, and this one is the carbon brush, and this one is the carbon brush you would have studied in class 10th, alternating current or AC generator. So, as soon as this coil is rotated with this handle, you will see that galvanometer connected to this terminal will get deflected. So mechanical energy is imparted or provided in order to rotate this handle or this coil, and ultimately electrical energy is obtained as output. So mechanical energy input to the generator turns the coil in the magnetic field. Mechanical energy input to a generator turns the coil in the magnetic field, and as a result, a voltage proportional to the rate of change of area facing the magnetic field lines generates in the coil. This is an example of Faraday's law, and on this principle electric generator works. So you see here, this is the solenoid, this is also a solenoid, but you see this solenoid is connected with the battery and also with a variable resistance, but this solenoid is not connected with the battery. But if you connect here a galvanometer and you change the resistance in this circuit, you will see that galvanometer in this circuit will change. How? Although these two coils are not in contact with each other, but these two coils are arranged coaxially, but they are not in physical contact. But still, whenever there is a change in current in this coil, current get induced in this coil. Because of changing current in this coil, magnetic flux or magnetic field produced by this coil also changes and is linked with this coil, and hence current get induced in this coil. As you move this coil away from this coil, then possibility of inducing current will go on decreasing, because magnetic field, as it moves away from this coil, magnetic field produced by this coil is not linked with this coil. So next you see here, there is only one coil and terminal of the coil is connected with the galvanometer. You see here, no battery is there, but as soon as magnet is moves into and out, then pointer of galvanometer deflect, indicating that current get induced in the coil due to movement of magnet. So work done in moving the magnet in and out is converted into electrical energy. So a magnet moving past a stationary conductor or coil causes induced current in the coil. A conductor moving through the stationary magnetic field also causes induced current or induced EMF. So either coil is moving relative to magnet or magnet is moving relative to coil. In both the cases, current get induced. So conclusion is that whenever there is a relative motion between the conductor and the magnet, permanent magnet or external magnetic field, current get induced in the coil. Next, electromagnetic induction is a consequence of conservation of energy. Without doing external work, we will not be able to produce electric current by the induction method. So in order to produce magnetic electric current or induced EMF, we have to do mechanical work, and that work done is converted into electrical energy. So work done to the magnet is just equal to the energy generated in the circuit to which the coil is connected. So we have concluded that the mechanical work is just equal to electrical. Even you can say the mechanical energy given as input is just equal to electrical energy obtained as output. So it obeys energy conservation principle. You see here induced voltage. What is induced voltage? We have already discussed that whenever there is a relative motion between the conductors and the magnetic field, the current get induced in the conductor, and hence voltage developed across the end of the conductor is called induced voltage, and induced voltage depends on a speed of the wire traversing the magnetic field lines. That is, quicker motion induces a greater voltage, because you know well that if quicker motion is there in the coil or a conductor, means higher kinetic energy is there in the conductor, higher mechanical energy is there in the conductor, so higher voltage get induced as output. Then, and next factor is that number of turns, number of loops of wire that moves in a magnetic field also causes the EMF induced in the coil. More is the number of loops there, more voltage or EMF will be induced in the coil. So the voltage is proportional to the number of loops. So as you increase the number of loops in the coil, voltage will go on increasing. Again, you see here induced voltage. If coil does not form a complete circuit, what will happen? If coil does not form a complete circuit, then what will happen? Try to understand. There is no complete circuit because this end of the coil and this end of the coil are not in contact with each other. So circuit is broken. And in that case, if you move the magnets back and forth or inside out, then what will happen? So you see here, induced voltage without current, no work to plunge the magnet into the coil. In that case, induced voltage without current, voltage will get induced because the two terminals will be plus and minus. But in that case, no work to plunge the magnet into the coil. And hence no current is there as circuit is not complete, but EMF will be there across the end of the coil. And now galvanometer is connected here, you see, or ammeter is connected. Then you will see this is not ammeter, this is actually galvanometer, because ammeter has no zero calibration in at the mid. Here zero calibration is at the mid. In ammeter, zero calibration is left side and higher calibration is at right side, but here zero calibration is here, so it is not ammeter but it is galvanometer. And you know that galvanometer can act as ammeter when a shunt resistance is connected in parallel with this. So right now we say this is a galvanometer, not ammeter. Here by mistake it is written as ammeter, but it is a galvanometer. Galvanometer is used to detect the current in the circuit. So as soon if the coil forms a complete circuit, what is the direction of induced current? Then we have to determine the direction of current. In this case, complete circuit is complete, so direction of current will be determined. Okay, so look at when magnet moves in and when magnet moves out. In both the case, direction of current will be an opposite to the two movement. Induced magnetic field is repelling, the current will flow in a way to create such a repel. We know that this magnet is moving towards this coil, so current in this coil will develop in such a way that this end of the coil will act as a north pole, so north pole and north pole will repel, so it will repel away this magnet. So movement of magnet will need effort to move into the coil. But as soon as you move away from this coil, then current in this coil get induced in such a way that it will attract this magnet. That means this end becomes south and this is north, so we will attract and oppose the far away movement of this magnet. Now, induced current, the more loop of the coil is there, the more voltage get induced in the coil. The more voltage induced in the coil, the more current through the resistor in the circuit will get developed. the more current through the coil, the stronger magnetic field it generated. So stronger the magnetic field generated, the stronger the repelling force acting back to the magnet, and hence a coil with more loop is a stronger electromagnet and push back harder. So in order to have a generator with higher output, we need a large number of turns of the coil and a strong source magnet. Next one is, you see here, induced current. What factors will affect the current induced in the coil? Let us check out. You see here, the induced voltage, current will depend on induced voltage. It will depend on the resistance of the coil and also depends on the resistance of the coil. Like you see here, this is the circuit corresponding to this, and this is the resistance. So when this magnet is moving into, current will move in one direction, and when it is moving away, the current will move in opposite direction. So try to understand here. Next, reactance. One more thing that you have to understand here. Three factors: induced voltage in the coil, resistance of the coil, and the reactance of the coils. Reactance we will discuss here. A coil has inductance, resistance. So effective resistance of the coil is called reactance. That will we will discuss in later topics right now. So there are three factors that will depend, that will cause the induced current to flow through the coil, and induced current depends on three factors that I have discussed here. Now, reactance is what? Reactance has same dimension as resistance. But if a circuit consists of resistors and inductors, then net resistance due to resistor and inductor is called reactance. Or in a circuit which consists of capacitor, inductor and resistors. So the net resistance is due to all the three passive elements, and this is called reactance. So similar to resistance, reactance depends on number of turns in the coil and also on the frequency of the alternating source. So resistance is independent of frequency, but reactance depends on frequency. Therefore, reactance for DC is meaningless. That means if you are being asked that what will be reactance of a circuit for DC current, then you must say that reactance is just equal to resistance. Reactance is just equal to resistance if DC circuit consists of only resistor in it. And if DC circuit consists of inductor, then the frequency of DC current is 0. Therefore, resistance due to inductor is 0. So net resistance is just equal to ohmic resistance in the circuit. So reactance is just equal to resistance for DC circuit. And this has already been discussed. Now, reactance, the counter EMF is the source of opposition to the current flow change. A constant DC current has a 0 rate of change and sees an inductor as a short circuit. So if a circuit consisting of inductor and DC current is supplied to there, this will act as a short circuit. An AC current has a time average rate of change. it is proportional to frequency. Therefore, it is proportional to frequency, and this causes increase in inductive reactance with frequency. That means inductive reactance increases with frequency. As frequency is zero, inductive reactance is zero. So I will discuss here in details reactance. Now, moving conductor in a magnetic field. You see here, this is north pole of a magnet and this is south pole of another magnet, and in between the space between the two poles, a conductor of a specified length is allowed to move in a direction perpendicular to magnetic field. So you see here the induced voltage of a moving conductor in a magnetic field. V equal to, this is voltage. Capital V is the voltage, a small v is the velocity of the conductor. You see here V. And B is the magnetic field between this north pole and this is south pole. And L is the length of the conductor. So voltage induced in the conductor is VBL. That means it depends on velocity of the conductor, depends on magnetic field, and depends on length of the conductor. If conductor is at rest, V is 0, then voltage induced in the conductor is 0. Now, as length increases, then voltage also will increase. As B, magnetic field strength between the region increases, voltage get increased. So this is the region. Induced voltage of a moving conductor in a magnetic field is given by this one. And you see here, EMF produced in this conductor is VBL sine theta. If theta is 90 degree for given speed and length, then magnetic EMF induced in the conductor will be maximum. For given speed and magnetic field and length. Now, on the basis of electromagnetic induction, Faraday's law of electromagnetic induction, we can frame out or generate or make a device that can produce or convert mechanical energy into electrical energy, and this device is called generator. So now we are talking about alternating generator, AC generator that gives alternating current. So here you see the principle is same. There is a coil, and inside the coil a magnet is moves in and out, and during that movement current get induced in the coil and appears as a deflection of pointer of the galvanometer. You see here the movement of magnet is alternating back and forth, therefore direction of current changes alternately. The induced voltage alternates on the direction of movement of magnet. If magnet keeps on moving in the same direction, then direction of current will not change. But here magnet moves back and forth, so direction of current changes alternately. Now, the greater the frequency of the field change, that means greater is the frequency of movement of the magnet back and forth, the greater the EMF induced in the coil. You see here, generator and alternating current. The frequency of induced alternating voltage is just equal to frequency of alternating magnetic field within the loops. Because as fast you move the magnet in the coil, you see here, if you move the magnet back and forth in 1 second 100 times, then a frequency of alternating current generated will be 100 Hertz. So if you move the magnet once inside and then back, one cycle is completed. So frequency is generated on the basis of the frequency of movement of magnet or frequency of change of magnetic field. You see here high frequency if you change if you change magnet back and forth very rapidly, briskly, then frequency will be higher, and pattern of alternating voltage will appear like this. If you move it slowly, then pattern will appear like this. This is crest and this is trough. So in alternating voltage pattern, there will be crest and trough. So this is just a sinusoidal wave. Now, generator, what is generator? An electric generator is a device that converts mechanical energy to electrical energy. As motor converts electrical energy into mechanical energy, so generator converts mechanical energy into electrical energy. So generator is just reverse of electric motor, but construction, structure, everything is same. Only difference is that in electric motor, we give electric current or electrical energy as input and get output as a mechanical energy. On the other hand, in generator, we give mechanical energy as input and get electrical energy as output. Only difference is that. So now, so far we have learned about the Fleming's left-hand rule, but here in case of induced current, we will apply Fleming's right-hand rule. Fleming's left-hand rule is used to determine direction of magnetic force acting on the current carrying conductor in an external magnetic field. But Fleming's right-hand rule is used to determine the direction of induced current in a conductor when it is moving in a magnetic field. So when a closed conductor loop is moved in a magnetic field, an induced current flows through it, and the direction of current induced in the conductor is given by Fleming's right hand generator rule. We say it is right hand generator rule, and everything will remain same as in the previous case. Fleming's left hand rule we use to stretch three fingers of the left hand mutually perpendicular to each other in such a way that forefinger would indicate direction of magnetic field and middle finger would give the direction of electric current, then thumb would give the direction of magnetic force acting on the conductor. But here we will change the hand. Instead of left hand, we will take right hand and stretch the three fingers, forefinger, middle finger and thumb of the right hand mutually perpendicular to each other in such a way that forefinger would pointing in the direction of magnetic field and thumb would point in the direction of force. Then middle finger would give you the direction of current induced in the conductor. This is the so simple method to determine the direction of current. What is the direction of induced current? These things has already been discussed, so let us check. As you rotate this coil with the handle, the direction of current induced in the coil will depend on the direction of rotation of the coils. If the direction of rotation of the coil is changed, direction of current in the coil gets changed. So you see here, right now, current in the coil flows clockwise and as the number of magnetic field lines within the loop changes, the magnitude and direction of the induced voltage and current also changes. Once again, try to understand. When you rotate this clockwise and anti-clockwise, you will see that current change their direction. Current change its direction. So mechanical energy, this is has all has already been discussed, and a voltage proportional to the rate of change of field is generated in the coil, and this is an example of Faraday's law. Now, uh, next one, as the number of magnetic field lines within the loop changes, the magnetic magnitude and direction of induced voltage and current also changes. You see here, this is the U-shaped magnet. Red one is the north pole and green one is the south pole. And in between these two poles, a coil is placed there, and there are two commutative rings. So it is nothing but what? Alternating generator. So as it is rotated with the handle provided, current starts flowing, and that is observed here, deflection of pointer here. So right now you see the position of coil. That means magnetic field line exactly perpendicular to the area of the plane of the area of the loop. And here you see that magnetic field line is parallel to the plane of area of the, and here you see again parallel, and here maximum. So in a complete cycle, magnetic current induced in the coil will increases in a particular direction and then decreases for a half cycle, and again then increases in a reverse direction and becomes maximum, and then again decreases to zero. And when it reaches to the initial position, then becomes one cycle completed. So here it is started from here and come to zero, and then increases in negative direction, and then again come to zero, and again reach here, then becomes one cycle. So try to understand here, a generator, alternating current. Once complete rotation of loop produces one complete cycle in voltage and current. You see here, this is the first position of the loop, this is the second position, and third, fourth, and again fifth position returns to initial position. You see here, current is zero in this position, EMF is zero, and this position maximum, in this position again zero, and in this position maximum but in reverse direction, and again zero. So one cycle is completed. So we see here in alternating current, it has started with zero and becomes maximum, and then decreases to zero, and again then increases to negative direction in opposite direction and becomes maximum, and again decreases to zero. So this is called one cycle. And the period time taken